today we're talking about AI and how you can integrate AI into your dApps. Why are we talking about AI? Because that's also one of the tracks for the Hyperdrive hackathon. And I'm going to just jump right into it. But before we jump into it, I actually want to just make a quick shout out to the build station because, well, we're hosting another build station in a few weeks. Chris, when is it starting again? 28th of September?
It's starting on the 25th, 25th. So next Monday. Next Monday, we're starting in Berlin with a build station until October 16th. It is going to be a whole lot of fun and a whole lot of building. 25th of September, next Monday.
If you're an artist, if you're a developer, if you're a founder, whatever, just come there. We also have a demo day on the last day, on the 16th of October, and there is a prize pool of 35K, as far as I know. Is that right?
Yes, sir. 35 plus, actually. Because
35 plus K. And well, we got a lot of sponsors. So if I was you, I would definitely come, demo your project. You have good chances of winning something because it's small. It's a small circle. So even if you don't win at the global hackathon, you can still win something at the local hackathon, right? And yeah. So what are we going to build today? Or what am I going to demo to you guys today? Is this Jupyter AI swap application. And I'm actually gonna make a quick demo of the real app because it's can actually go and use it. So once you launch that app, you can just connect our wallet. With my browser. So we can just connect our wallet. This. And now once we're here, or maybe let's use Solver because it has a better transaction simulation. There we go. We can swap, let's say, one USDC to Euro E, and then it will take a few seconds, 2, 3, 4, 5 seconds, and then it will give us the actual transaction that we can then execute or not. Well, in theory, you've probably seen the tweet. We have the demo effect. So I'm just gonna show you this video. Can, for example, swap one USDC to Euro E, and then it will show us this cute little block, and we can just execute it and then sign the transaction, and that will actually just call the Jupyter program and swap one USDC to Euro E, and then we can just do the same but vice versa, and it will generate the transaction for us. So we can essentially convert from natural language to like an actually executable web like transaction, Solana transaction. And that's what we're going to do today. So you can see on the screenshot as well, 0.1 sold to Samo. And well, then it just shows us the pop-up and we can approve. So how's it going to work? Well, of course we have the server and the client. So on the client, the user sends his whatever he wants to swap. And then we call an endpoint on the server. And on there, the server fetches all the token balances on our wallet. So if we want to do a swap, we essentially want to give the AI less options, or we want to give it as accurate options as possible. And obviously we can't swap any tokens that we don't have on our wallet. So while we're limiting the tokens, the input tokens that we want to swap from to the tokens that are on our wallet. And then, well, as I said, we're just putting all the tokens that we have on our wallet into a vector database, and then we're well, querying the vector database for the one that is most likely the one that the user is searching for. So we're putting in the prompt, and let's say on the prompt that says USDC, then it's going to look for tokens that have a similar name or symbol or whatever to USDC. And then we are also doing the same thing for the tokens that the user wants to swap to. So we have a JSON or a vector store as well with all the with the Jupyter token list. So all the tokens that are listed on Jupyter. And then it does the same thing. It just does a query through the vector store to find the tokens, or like the top 5 tokens, I think, that are most likely to be the one that the user is referring to. And we're just giving our top 5 from the input tokens and the output tokens to the AI, and the AI evaluates the results and also gives it the amount that we want, like how many do we want to swap. So it extracts that from the user's prompt, and then it at the end returns a JSON response, like with the mint from the token that we want to swap from, then the token that we want to swap to, the mint address, and then the amount, how many we want to swap. So that it sounds a little complicated, but I think when we get to the code, it will make much more sense. So don't worry. And well, once we got the JSON on the client, we're just doing some, we're handling the data, putting it in some Jupyter functions, helper functions, and then we just sign the transaction. Now, what the fuck are vector stores? They're databases that are used to store vector embeddings. And now you're asking yourself, what are vector embeddings? Another weird word. And vector embeddings are used to represent relationships between data points. So, for example, it's used with natural language processing, semantic search, or recommendation systems. Now, how can I imagine vector database? We all like graphs. So this is how you can imagine a vector database works. There's like these similarities between different vector embeddings, and the AI kind of looks or does similarity searches and returns the ones that are most likely to be the one that you're referencing to. Now, I just want to jump into the code and just want to show you around, and you'll hopefully understand everything better. So let me open VS Code really quick. Now, there we go. All right. So as you can see on the actual app, we have this card in the center. And here we just have this input bar, the button, and then the messages once we enter them, and obviously the usual wallet connect stuff. Now, where's our code again? There you go. We're going to start with the AI input. So I'm not really going to go too much through the React code, because I think that's not really what we're focusing on here. It's essentially just a basic React code base. So here we have the AI input. And what we're using here to simplify everything is a package called LangChain, and we're using the Versal AI package. So both these packages can be used to simplify all your AI stuff, because they provide a lot of utility functions and helpers, and they integrate third-party tools to simplify connecting all these different services. Now here, what we got here is from the AI package, it's just a hook called use chat. And this one, we're just passing in the API endpoint that we want to call, which is this one. We're giving it an ID to share the state of the use chat composable between different components. So if we want to access it in the chat.tsx, we also give it the ID one, then we can access the same values here. And body means we're passing additional data to the JSON body that we're sending to the API. And we want to give it our public key because we later need to fetch the user's balances. Now, these things, it's just an input, handle input change, handle submit, and is loading. These pretty easy. You just put them in your text field. So You don't have to create your own states or whatever, and it's all provided. So on change and input, you just put them in here. And then you also have the on submit. So when you press enter, it does the API request with your input, right? And is loading, I think, is pretty self-explanatory. While the request is, or while the AI is still answering and streaming the response, is loading is true. And obviously we don't want the user to be able to ask another question or another swap while the AI is busy. So the more complex part is probably the chat.tsx file. And in here, we also, again, have the use chat hook, right? But this time we have messages here. So messages is, when we go here, you can already see the fields, content, role, and things like that. So when the user asks something in the chat, that gets added to the messages array. When the AI answers, that gets added to the messages array. And we can always check who sent the message with role. And then it gives us assistant or user. We can ignore function and system. We don't really need them for this one. But user is, well, the user, and assistant is the AI. Now I actually want to jump into the API route first. So what we got here is a post request, and we are getting the messages and the address of the user from the well, request body. So it's a post request. And if you remember, we defined the address in here so that we want to pass in the address in the route, in the use chat hook in the AI input file. And now we're extracting it here, and also messages is also always included by default when we are using the use chat hook. So that's provided by Vercel or Vercel's AI package. And now the prompt of the user is always the latest message, because now we send the message and we pass all the messages to the server. Then the most recent message is the one the user sent. So the content of the last message is the prompt. And now we're coming to the first LangChain reference. As I said, LangChain is a tool to simplify all your AI workflows, because it integrates all these third parties into one single node package or NPM package. And here we have this use LangChain stream class, which we're initializing, and we can get a stream and handlers from here. And stream is just the socket that we're returning here. So the response of the AI. I mean, you know it, when you're using ChatGPT, it doesn't return the response at once, but it always adds a few words at a time until the response is complete, and that's exactly what we're doing here as well. And the handlers, what are the handlers? We are using them later, so I'll show you then. But now the first thing we're going to do logic-wise is we're getting the user balances, as I already mentioned earlier. So that all includes the SOL balance and the SPL token balance. And now in here, we are checking if the user has any tokens first. So if he has any SPL tokens or native SOL. And if so, we are loading a vector store. And this vector store is it is stored in here. So that's how it looks like, or what it looks like. Nothing really that you need. This is just a JSON with all the tokens on Jupyter that are listed on Jupyter, and some other files that are needed for the similarity searches. How do you create these vector stores? I mean, when you are first initializing them or when you create them, it looks kind of like this. So instead of HNSW lib, you have from documents, and then in here we can put in all the or read a JSON file with all the Jupyter tokens, or fetch them from an API. And then documents is just a type. So we're essentially just putting in the content, so the token list consists of a list of tokens with mint addresses and logos and whatnot. And we're just putting in the documents in here. And then we're choosing a embeddings provider. So OpenAI can create embeddings for you. Again, this is for essentially being able to put that information into a vector store, because the information is not a plain text in that store or in that database. It's converted into vectors, as I mentioned earlier, to enable things like this vector search. And now, once we kind of have this vector store, right? I'm just not gonna put in anything here. Like this, you can just store.safe and then give it a path. So that's what you do once. And once you have that store, you can just reuse it if you don't have to change it. And because I've already created it now, I can just do load, and then we're just calculating the path and also the way we want to get the vector embeddings. Now, what is this thing? That's one of 1,000 vector store providers. This is the most simple one because it's locally. You maybe have heard of Supabase vector stores, or ChromaDB, or Pinecone, or Fice. These are all options. It's totally up to you. It doesn't make really a big difference. The only big difference with this one is that it's locally, as I said. But for example, Supabase would be on the cloud, which is of course better in production usually if you want to update the vector store. So that's it with the vector stores for now, how we initialize them and create them. And now here, as I said, we have two searches that we do. So one is for the tokens that we can have as an input, and the ones that we can have as an output. So let's say we want to swap one USDC to EUROE, then USDC is our input token and EUROE is the output token. And for the input token, as I said, we can only use the ones that are on our wallet. So we fetched our balances earlier here, and now we're going or creating a filter function where it checks whether the documents in the vector store or it filters for the documents with the mint IDs that also are on our wallet. So that only tokens that are on our wallet come into question. This filter, we're just passing it into our similarity search. So as you can see, store is our vector store that we loaded here. And now we can just call the similarity search function, put in our prompt from the user, which could be, for example, swap one sol to bonk. And 3 means we want 3 results. So it gives us the 3 results with the highest similarity score. And now the third thing, we're just passing in the filter. So we predefined it here just for readability, and then we're passing it in here. We could also just write the code and filter instead of this, right? It goes through all the docs in the vector store, and the ones that don't, that return false are excluded from the similarity search. Now, the tokens that we want to swap to, there isn't really a filter option because we can swap into all the tokens that are available on Jupyter, or that's what we want in this case. The user should be able to swap to all the tokens that are listed on Jupyter. So we are not adding a filter, but because the results can be more vague, we are adding more results, or we want to have more results. For example, there can be 6 coins on Jupyter that are called something with bonk, right? And we want to return multiple due to that reason, and not just the first one, so that the AI at the end can evaluate all these results to find the best one that matches the user's prompt, because the AI at the end is smarter than a vector store. Why are we using vector stores then? because we can't just put 6,000 tokens into the AI prompt, because one, that's expensive, and second, that's probably not even possible with the token amount that we can input in the prompt. Now, once we got the from tokens and the to tokens, so the input and output token options, we're just putting that into this variable so that we can put that into the AI's prompt. Now, what the hell is this again? The chain, this is our conversation chain. So essentially a class that we're using to when we have a chat with the AI. So we have this helper function make chain. In here, we define the model that we want to use. So we are using the OpenAI ChatGPT model, GPT 3.5 Turbo. Temperature, frequency penalty, and all that, we can set that in here. And also streaming means, do we want to stream the response, or do we want to return it at once? We want to stream it, of course. And also the callback manager, where you can just handle errors and things. That's it, actually. And now the chain, that's the relevant part. There are lots of different chains that you can use. There are like tens of different types for summaries, for conversations with better memory and automated agents and everything. That's also functionality provided by LangChain. And here we just pass in our model. The memory, that's a little bit more complicated. I'm not going to get into that. That's not super relevant for now. And then the prompt that we are giving the model, because we're not just giving the AI model the prompt of the user, but we also give it a template, right? And our template is this one. So it says, you are Jupiter AI. Jupiter is a liquidity aggregator and offers token swaps and whatever. And then the user will ask you to swap tokens, for example, this. You are given some context. The context contains a few JSONs of tokens and their metadata. It's just to instruct the AI what to do, what not to do, what it can expect, what it should respond with. So for example, we said your JSON response should look like this. And then we are passing in a JSON example. So this is what it should look like: the from address, the to address, and the swap amount. And then the user's question is going to be in here. So the question is actually, or the prompt of the user is actually one of the, like the smallest part in the whole prompt, in the total prompt. And the context, what's the context? That's actually also the most relevant part. This is where the results of the vector stores will be shown at. So our from and to tokens that were queried with the similarity searches, these are going to be placed here. So all these that are surrounded with braces, these are variables that we can parse in. I can actually show you here at the route again. So we are passing it in here. There's a function called partial on the prompt, and well, there's just the example and the context. And if you remember, there's also the question, but the question gets passed in automatically, so we don't have to worry about that. We just need to pass in the JSON example and the context. Yeah, you might be asking yourself, why don't we just put this small part right in here? And that's because when we want to show it, okay, you should return a JSON like this, we usually have curly braces, right? But when we have curly braces, it thinks that there is a variable, so it throws an error at runtime that we haven't passed in this variable and stuff. So whenever you want to use anything in your prompt that has curly braces, you have to pass it in as a variable. Now we have the chain, right? So now that we have the chain where we have the model, the memory, the prompt configuration, we can just call the chain with the user's question And we're also passing the callbacks, so the handlers. That's what I was showing you earlier here from the LangChain stream. The handlers consist of a bunch of functions like what to do when we get a new token, so new characters essentially, when the LLM ends, when there's an error and stuff. And thankfully, the Versal AI package handles all that for us, so we just have to pass the handlers in, and that's it. As long as we use the package's streaming text response class, which is also from the Versal AI package. We just return this, and we don't have to worry about WebSockets or anything else, which makes it very easy for us, especially when working with unconventional backends like the Next.js server route or the Next API route or anything likewise. Now this is it actually for our backend or for the AI interactions. We also have this little route where we are fetching token metadata, but I will get into that in a bit. It's nothing complicated. The only thing that's left now is this chat.tsx file, where we actually have the whole chat UI, except the input, which is in the AI input that we already went through. Now here, as I showed you, we also have the use chat hook with the API route that we just went through, and we just get it. We have the messages, and we can check whether it's loading or not. And here we have 1 second. There we are. Right. So we're checking when the AI is still loading, we're showing a skeleton. So just like a little shimmering effect on a square. So like this, swap 1 USDC to Euro E. This thing here, that's the skeleton. And now when it's not loading, we are looping through the messages, and we're checking when the role of the message is user. So when the user sent that message, we're returning a different component, because for the user we just have a conventional message like this, and for the AI we have this swap block that I showed you in the video, which is here. And here we're checking if metadata for the message ID is not null. If it is null, we don't show it. So that means it's still loading. And if it's there, we're rendering it. I'll show you the code for the state in a bit, how we get it and all that. And in here, yeah, it's just the component. We have the image of the token that we're swapping from, the name, then the amount that we're swapping, this token we're swapping to, and a button if we want to execute the transaction again. So this actually calls the show swap tx function, which is the last part of our code. Now, before I go into that, I first want to show you this thing, what we just had in the JSX. This is just a little map. So we are mapping the token data for each message inside of the state. So it could look like this. For the message with the ID 1, we have the, I think Copilot's doing something. Yeah, right, okay. Yeah, we have like all the token data that we need to show it in the UI. Now, you could be asking, why aren't we just putting the token data in the streaming response with the AI? Because the AI has the knowledge, essentially, since it's all in the metadata on the Jupyter token list. Why don't we return the image, the decimals, the symbol, the name with that? The reason is that the shorter our response in this case, the better, because the AI needs, the more tokens that it has to respond with, the longer it takes to respond, right? So ideally, we want to just let it handle as few things as possible, and the things that we can do on the client, we want to do on the client, like fetching token metadata, like images, because writing URLs, especially since URLs are pretty long, it can take the response time from 5 seconds to 20 or 30 seconds. So for that reason, we're just returning the amount and then the two token addresses. And there we are. So here we're just mapping the message IDs to the token data. And there we are, right? Here we have the function to get the metadata. Here we're calling our API endpoint. And on that API endpoint, we're just calling the Helios API. It just returns us all the token metadata, again, name, decimals, image, symbol, all that. Why aren't we just calling the Helios API from the client? That's because I don't want to, or we don't want to leak the API key or our Helios API key on the client, because you could extract it from the networks tab. So we are routing the request through the backend. There are better ways with JVT and whatever, but we did it for like this for this demo. Right, so we're passing in the mint accounts, so the from address and the to address, and it returns us the data. Now we are calling this in here. This is a use effect, and in this use effect, we are looking when the assistant has sent us a new message. So when we asked it and it has finally, well, it's done with the answer or with the swap JSON, right? This gets called, this piece of code, and we are first converting the last message to a swap or an AI response. So we are parsing the content and typing it. Now, this looks really complicated, but it's really simple. It's just we get the metadata, like I just showed you. We have the from address and the to address. We fetch the metadata, and then with the metadata, we want to set the map. So the metadata for message, and then for the last AI message, we want to set all the token data that we need so that we can display it in the UI. And this is just the Helios response. Here are some fallbacks if there are different token standards and stuff. Nothing really to worry about. It's just a lot of text, repetitive text. And once we got the metadata and everything is ready to be rendered on the UI, we are showing the swap transaction, which is, there we go. Here. Here we are just getting the quote. This is, if you want to learn more about the Jupyter API, they have pretty good docs, so you can check it out there. I'm just gonna fly over it really quick. So we're getting the best routes for token swap and doing an API request to Jupyter. So we're passing our input mint, our output mint, and the amount that we want to swap, as well as this maximum slippage, which is 0.5%, I think here. Now we have the routes, and the routes is what we need to get the actual swap transaction base64 string. So that's also another API request. This time it's a post request, Jupyter/swap. And we're passing in our route, the public key of the user, and then also we wanted to wrap unwrap sol. So essentially we don't have to have wrapped sol to do token swaps with sol as input. Now, here we are also returning the swap transaction result. And to get the base64 transaction string, we are first doing buffer.from, and then we are deserializing the transaction. So it's a random base64 string at first, and then we can just use the Web3 package with the version transaction, and it has a deserialize function that takes a uint8 array, so a buffer. And now we finally have our transaction object, and we can just pass it into the signed transaction function from the wallet adapter. And yeah, that's it. That will show the transaction pop-up. And that's how we converted our natural language prompt into a actual transaction that we can run and sign on chain. So again, just a quick recap. First, the user sends a prompt. On the back end, we're doing some vector store querying. So we're checking, okay, which tokens does the user want to swap? Which tokens have a similar name to the things that the user mentioned in the prompt? So it's much about keywords and similarity searches, similarity scores. So if the user said USDC and we have a coin called USD and we have a coin called USD coin, which one is more similar? Which one are we going to return? Then we want to put all that into the prompt to the AI. We give it some prompting, some instructions, things to do, not to do. And at the end, we wanted to return a JSON object. The one caveat is, of course, that it takes longer to wait for the AI's response. So waiting, it's not the fastest thing. So you really have to think about when to use it and when not. Is it really worth it that this process takes 5 seconds longer than it would be if the user selects the tokens manually? And when we return the JSON object on the client, we do some processing again. We take the JSON object, do the API requests, and then finally get the actual transaction buffer or the basic C4 string to convert into a version transaction, and then finally sign it. So it sounds very complicated, but as you can see, it actually is not really. It's maybe 200, 300 lines of code of logic. So it's actually just this part, and then this as well as the langchain.file. So it's really not that complicated. If you've done it once or twice, you get in the flow. There's a lot of reusable code. I also open source this on my GitHub. So yeah,